let's continue our discussion last time on motion control. I think we start talking about defines what motion control problem means, and we're trying to we reviewed a little bit about linear control design, and most of the robotic control problems, motion control problems, are done through linear control design. Okay, and the reason we can do it is because the robotic system is a nonlinear, highly nonlinear. The reason we can do it is because of the special way we kind of linearize the system. It's typically called a feedback linearization approach. Okay, I wouldn't introduce a general theory of a feedback linearization, but I will give you a little bit more intuitive way to introduce those methods. I think last time we start talking about velocity resolved case. I think it has been a week since we have more time. So let's try to explain the concept more carefully. Okay. So last time we introduced the motion control problem. Okay. What does the problem means is that we're given a robot, okay, and depending on a particular robotic system or depending on your assumption, and the robot may accept or take different input, and you may care about different output, maybe joint position, joint velocities, or task space variables. So U and Y may mean different things, but in general, the motion control problem is design or compute the input U to let Y, the output, track a desired reference. Okay, which is what I call YD, and this desired reference YD is given by planar. Okay, how to design this YD, we don't talk about them for motion control. That's more like a motion planning problem. But sometimes these two problems are kind of coupled or there's overlaps. But let's make sure our problem is clearly defined. Just try to make sure there's given YD that you want to track, and you design U to achieve that. Okay. As I mentioned last time, depending on our assumptions on this U and Y, let me use that, U and Y, and the problem may appear quite differently, but you don't need a different theory to do that. All you need is linear control design tools. Let me repeat, most of the motion control problems you may encounter in the future, or you see from textbook, most of them should just mainly depend on or rely on the linear control design method. Okay, typically we can categorize them, let's say, depending on the output meaning. All right, so if the output means, if we care about output in terms of joint variables, here I call it Q in Rn, this is joint variable, right? Particular joint variable, that's this we call that, we can refer them to joint space motion control. Okay, all we care is individual joints need to track a given joint angle reference or velocity reference. Okay, another category is that Y correspond to some kind of a task variables. Okay, maybe I call that T and Q. In SE3, that means the entire configuration of the anti-factor frame. Or my notation was like this. Okay, that's well defines maybe some kind of a task space variable. May not be the entire frame pose, maybe the origin of the anti-factor frame. If you have a leg robot, quadruped, there's have a point foot, right? You don't care about orientation, you just care about the location of the point foot. Okay, that's a task space variable, right? That depends on the joint variable, but not but through some forward kinematics relations. Okay. Task variable, for example, the origin of an effector frame. Okay. If in this case, we call that task space motion control. So the quantity of our interest is directly specified in the task space, not in terms of joint. Okay, that's depending on the output. And further, I introduced 3 different categories for input, right? And the input typical assumptions could be Q dot is our U. You can directly specify the joint velocity. You can directly control the joint velocity. That's a assumption. Or some robot, you can directly have velocity control mode, okay, for each joint. So this is a Rn, right? Or you can directly specify the acceleration of joint. This is a purely a abstraction, or I don't think most industrial robots don't allow you to directly control acceleration. They have a position control mode, velocity control mode, and torque control mode, or current control mode. But it's not really acceleration. But acceleration is really important abstraction. Well, we will see that later today, hopefully. Okay, and another one is directly control torque. You can directly control torque, and these two are equivalent almost. But one requires you to know, if you want to know torque or use torque to control motion, you have to know precisely the dynamics. Torque means force, almost like, right? If you want to use force to control motion, you have to know the dynamics. Like F equal to ma. If you want to use F to control A, you have to know M. Okay, so that's the difference. But if you directly control A, you don't need to know M. You just directly control the motion. Suppose that can be measured. Okay, so the name is that I call them velocity resolved case. Let me write it down. Joint space control. That's velocity resolved case. This is the acceleration resolved case. Joint control, joint space control. Okay, this is just torque control. So the lowest level you can get with torque. Okay, that's the lowest level. That's equivalent to current of the motor. But what we mean by velocity resolved case is some kind of modeling assumption is that you can directly specify desired velocity, desired acceleration, and some internal mechanism, internal controller of the robot can take care of that control part. Eventually, everything goes to torque. Okay, I will draw a few figures. I think you should be clear later. Okay, and the same thing happens here. Also 3-part. Okay, the first one is Q dot. We can directly control Q dot, or directly control Q double dot, or directly control the torque. Okay, and correspondingly, we will call that velocity resolved task space motion control. I will just say control dot 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 dot. Okay, I don't want to write everything out, but you should know roughly the structure. That's how I categorize them in my mind. I didn't see any textbook talk like this, but all of them are based on one simple linear control tracking method. Okay, that's get to. You just need to know one method. You can work on different categories of problems. The method we introduced last time, let me briefly review a little bit. That's the simplest case, and that's the only case you need to know. All the other case can be somehow transferred to this case. Okay, simplest case, let's call that joint space velocity resolved. What we mean is that we want to directly control, we are given a joint reference. We directly control the joint, we are given the joint reference. Okay, the planning part directly plan the joint reference, and that means y equal to q. Okay, the output variable is q, and u equals to q dot. Okay, typically, if you want to be more precise, let me explain that a little bit. I think some people are confused by that. What I really mean is the following: is so that's the model, and if these two holds, then that means y dot equal to u. You see what I mean? You can directly change the velocity of y, and this is in Rn if you have n joint. Okay, that's this part. So I will have a remark here. This model makes sense. Makes sense if what? If your robot can truly kind of control that, directly control the velocity. So if for any given, all right, u, which is the velocity command, and the joint velocity q dot can immediately reach this u, the command. But this is typically done, which is due to some internal controller, okay, like driver. You specify the joint velocity, that's abstraction, right? There's something happen in the motor, in the servo motor, or in the robotic arm, and there's some controller will help you do that. For example, if you say I want to have a u here, and let me draw this. So this is my u, which is somehow a velocity q dot command, if I write like that. And I say this is the robot, but inside the robot, actually, there's some kind of controller here, and will generate torque to the robot. This is robot. There's some feedback here. And make sure that this controller, internal controller, can achieve that desired velocity instantaneously. You ignore any kind of transient of that part. In other words, suppose this is my q dot, I choose q dot. Okay, this is the time, and this is maybe my command. This is my u, let's say the command, velocity command. Okay, and the actual response, maybe velocity may have some tracking like this. All right. By taking this model from outside of the robot, I assume that this guy can track. All right. We somehow think this is that. That's our true response. It immediately follow that. I ignore any kind of dynamics for internal tracking of velocity command. I don't like this. So the actual response may be like this, but we ignore that. So we will say, let's do that. We will just say this is my ideal response. That's directly track whatever given reference. So from outside, from this input to output behavior, I can just assume, okay, whatever joint velocity you ask me to achieve, I can immediately achieve that. You don't need to ask how I do it, but that's my assumption. I think most of the servo motor or industrial robot, they have the velocity control mode. But if they don't, you assume you can design that first. Okay, that's the explanation. And then our problem is that given y desired, okay, in this case, it's just a QD, right? desired, the joint velocity, sorry, joint reference. So our design is this U equals to YD dot plus K some gain times the error, which is YD minus Y. YD is a given reference, and typically I explain that that's typically given by through kind of polynomials. You can also take derivative of it. So you have a derivative that's feed-forward term that has a feedback term, which depends on the current measurement of Y, which is Q in this case. And if you plug in, I call this one our model 1, let's say 1, right? You plug into 1, you will just get Y dot equal to YD dot plus KYD minus Y. And if we define Y tilde as YD minus Y, this guy is our error, we call that Y tilde, then eventually we will have Y tilde dot equal to negative K, move this to the left, right? Y tilde. You have a linear system, right? So under what condition this system is stable? Yangxing. Stable if negative K is a matrix, right? This is an n by n matrix. This gain matrix is Hurwitz. How to write Hurwitz? Hurwitz. Okay, that means the eigenvalue of this matrix lies on the open left half plane, what we introduced last time, right? In this case, not only have stable, but we know the error will eventually converge. A tilde t is e to the negative k t times y tilde 0. So no matter how far you're away from your reference at the beginning, eventually the error will convert to 0 exponentially if that guy is stable, right? This is clear? So then I can say I can achieve perfect tracking just by design linear controller. But there's some kind of, there's a catch, right? This assumption is based upon that whatever you tell them the joint velocity is, and the internal controller can achieve this joint velocity immediately. If that's not true, then this model is incorrect. Okay, and you cannot guarantee anything, but it's hopefully the response is fast enough so that this assumption is not exactly holds. It's something not exactly hold, but roughly holds. Okay, that's the hope. Okay. Remember this guy, right? So let's call that our law, control law, right? This is 2. Let's call this equation 2. Okay. Remember this thing. Okay. Now we have task space. First, task space velocity resolved. I think we started talking about this last time, but I was in a rush a little bit. So what we have is this is our U, this is a robot, this is Y, and this U is still the same assumption. It's Q dot. Okay, you can directly tell what the joint velocity is, and the robot can achieve that joint velocity immediately. That's the assumption we make. And this guy now, instead of I want to track a joint reference, I want to track YD, which is given in SE3 or in task space variables, okay? Or let's just say YD given in task space. The n-effector frame or whatever possible quantity you care about. Okay. So in this case, before we have a Y dot equal to U, but now we don't, right? The Y is this, and Y is something like FQ, okay, task space variable. Y dot will be J of A, Q, q dot, right? That's analytical Jacobian. If I want to say y it's IC3, then y dot is just a twist. But anyway, this is a more general than twist than the geometric Jacobian. Okay, this is our u, so I will have JAQ times u. Yonghan, is this a state space control system? Is this a state space control system? Yes, but not in this form yet, okay? What we typically like to see is fx equal to x dot is velocity depend on state and u only, does not depend on other variables. So if we have a state defined as y, then there's some other variable q that it's hard to tell their relation. So we have to eliminate q and represent everything in terms of state and control. So how do we do this? As I mentioned, the q is just ik of y. If you do any kind of task-based variable, you just need to, you can find, may not be unique one-to-one correspondence between task variable and join, but suppose there is a correspondence. Given y, I can find a q. In this way, I will say y dot equal to JA ik inverse kinematics, some formula q, y times u. This is our model. I think that we derived last time. This is our model 3. Yonghan, is this a state space nonlinear control system in the form, right? This is this where the state is y. You know y is, what's the dimension of y? I don't know, I didn't specify this in terms of general case. That's that, okay. Now the question is, how should we design control to do the nonlinear control? We don't know, we didn't learn how to do it. There are ways to do it. They're not elegant. I don't think there's a universal way to design nonlinear control, but there are universal ways to design linear controllers. So now I want you to see, can you see the difference between 1 and 3? One is what? One is y dot equal to u. And the other one is y dot equal to something times u. Mathematically, this could be the same under certain conditions if you change variables. What's the meaning of this? You can directly specify y dot. Okay, so whatever y dot you want to get to, you can directly specify it. Can you directly specify y dot here by choosing different u? It depends. If this multiplier, let's say if this coefficient matrix, this Jacobian matrix is 0, then you cannot. You can only have 0 velocity, right? It's really depending on this matrix. Okay, so I would say, let me make a comment, then I explain. I would say they are equivalent. These two models are mathematically the same if this JA, IK, Y at any given Y it's invertible. Okay, let me say a few words. So y dot equal to A is equivalent to say y dot equal to, let's say in scalar case, okay, suppose it's scalar, this is example. Equivalent to say y dot equal to 2u. Can you agree with that? Do you agree with this? This two has no kind of difference. Of course, the units are different, right? What about I say e to the y times u? Okay, these two are almost equivalent, right? I can say I can define a new variable which I call this guy something different. So whatever, because you want to say u equal to 2, here I can find, depending on where you are, I can find a u to achieve that. You see the meaning? Okay, so that's the key. Although this looks simple, this looks hard, this one looks complicated, but if you can generate arbitrary velocity of y, then I'm fine. Okay, so that's the idea. So let me specify that. Okay, I call that divide and conquer, right? The key for this one is I can directly control y dot. Now here, it looks I cannot directly control y dot direct. I don't know, it's a little bit hard to say, but let's introduce a virtual control, which is I call that v of y. Okay, so I will say suppose I can directly control the velocity of y. So this guy, this 3 can be saying that y dot equal to v of y. Suppose I can direct control that. Can I? That's under the condition and u equal to JA. Suppose I can inverse it, okay? Inverse times Vy. If I do this, the system will be the same, or the design methodology of this part will be the same. So whatever Vy you need, I can get to you. Owen, does that make sense to you or not? 对，可以啊 ，invert 嘛。不独立啊。It's different, but I think they're equivalent in terms of design things. Okay. So the system may not look like y dot equal to u, but I can introduce a virtual variable. Oh, anyway, so Bowen, do you think y this is equivalent to y dot equal to 2y? Oh, that's the same. If you can invert this guy, then it's fine. But that inversion, this coefficient is state dependent. That's the only thing. So at any given time, you just need to know the state. Then you invert it to find the u that you need. Okay. All right. So I think if you want to see that, I can draw a formula first. Draw the diagram. I think I draw the last time. Let me just, since you guys still have questions. So y desired get to this, our controller. And our controller divided into 2 parts now. This is our robot. I need to determine u, which is q dot. Okay, and the y is something that I care about in task space variable. I will say this guy is u equal to, let me say the example, okay? For example, u equal to JA inverse. JA may not be invertible. I'm just simplify the discussion. JA inverse y times Vy, and I determine Vy here. This is the same controller as previous case. What I mean is the simplest case. So if for any given Vy, I can choose U to match it, the given Vy, then from here to Y, here this part is Y dot equal to Vy. So give me Vy, I can choose a U to achieve that Vy. If this invertible, I can do this almost perfectly. So based on these two blocks coupled together, so the robot is not Y dot equal to Vy, but these two blocks connect together, the overall effect is just Y dot equal to Vy. Okay, because at any given time, it's just this inversion, Bowen, this inversion is state dependent. You can feedback this, right? You know this internal loop, right? So you know Y, suppose this is Y. You know Y at any given time, so you can invert it. So whatever desired velocity you need, I can always generate the right joint level velocity to achieve that Vy. So overall effect is Y dot equal to Vy. Okay, so overall I will call this guy, this is the example, but if this is a example, right? In general, let me redraw it again. YD is, I will call this, sorry, this guy is here, right? This is a Y desired as a reference. Here is, we call the outer loop control, okay? And which generate Vy. And if you need some Vy, okay, my inner loop will do it for you. I will try my best to do it for you, okay? So we'll try to generate U such that the velocity of Y equal to Vy, okay? And this U sent to robot, generate Y, and this is the inner loop, and from the outer loop, guys, is here, okay? So it's just, this part is my new robot model. I can assume I can directly specify the velocity of Y. Okay, so what should we design this outer loop? What is the outer loop? This part is the same as the previous one, right? So, so we can design this. We can design this controller, the outer loop controller, as if we can directly control, I would say directly control velocity of Y. Okay, in that sense, I would say this will be my control now, right? Vy equal to yd dot plus k times yd minus y, the measurement, which is the same as equation 2, or what, which one I call it? Equation 2, right? Just assume you can direct control velocity. Just making this assumption. That's your job. That's the outer loop control job. Just assume you can direct control velocity, and you throw the hard part to the inner loop controller, okay? I assume you can take care of the rest. Suppose I can direct control velocity, you just need to tell me how you work really hard to meet my requirement to achieve the desired velocity I sent to you, okay? That's the inner loop job. Okay, in this way, we will have, again, Y tilde. Because of, okay, this you plug into what? This guy, okay? Into Y dot equal to Vy, that's my assumption. Then I will have Y tilde dot equal to negative k y tilde. Under the assumption of what? We are making the same assumption. That's all I want to say. Here, the reason I can achieve this, I can say I can perfectly track, is whatever joint velocity I tell the robot to do to track, the joint velocity can be perfectly tracked instantaneously. That's the assumption we make. Okay, but now we just say that, okay, this also work if whatever task space velocity I tell the robot to track, the robot can produce that task variable velocity. I don't care how you produce it, but if that assumption makes sense, my outer loop can be designed this way. Okay, and then the inner loop will work really hard. Try to, it's divide conquer, right? You make the problem into two phases. The first phase, I just need to design the desired velocity, and the inner loop will work really hard to meet that demand. Okay, so that's the inner loop case. I need more space. Okay. Bowen, does it make sense to you now, or still a little bit? Okay, now let's use another color to tell you the inner loop guy. How do we design this guy? What's the purpose of inner loop? Bowen, what's the purpose of the inner loop? Let's call it objective of inner loop is to determine, let me just, let's determine my actual U, okay, the U, which is Q dot, such that my actual Y as close as possible to Vy. You see what I mean? That's the objective. We somehow decouple the design to two phases, all right? The first phase, I assume I can directly control the velocity. Of course, this assumption depends on how hard the inner loop guy can work, okay? So the inner loop will try really hard to make sure I can design the actual control input to the robot such that Y dot is meet whatever Vy that you determined, okay? So of course, for example, well, we can do this, right? For example, I can let, so we can let what? U, because we know Y dot equal to what? It's nonlinear, right? It's nonlinear. We know Y dot equal to JA of IK. That's a Q, okay? Q is known at this time. Times U, right? That's a relation. All we want is that you tell me Vy now, at least instantaneously, you tell me a velocity you want to achieve, and I will try my best to do it for you. So I will say U equal to JA per pseudo inverse times Vy. Does this make sense? Pseudo inverse means sometimes you get perfect match this if possible. If not, then you minimize the means the error, the squared error. Right? That's one simple example. Or you do a little bit more involved case. I said you try your best to meet the outer loop command. You cannot do arbitrary things if that's not feasible, right? Or you can compute U by solving the optimization problem we somehow mentioned it, minimize over U. I want choose this guy to make sure Y dot closely equal to closely approximate Vy, right? So our goal is Vy is given minus JAQ U squared, right? And I may subject to some constraints on U. Try your best, but sometimes some task is infeasible, right? If I give you one lecture on MPC, I don't think you can truly understand anything. It's something is infeasible. So constraint can be, for example, I'm just giving you an example, not saying you have to follow this. Example is that U less than Q, what does U mean? Q dot, right? Less than Q dot max, minimize min Q dot. That's some kind of a velocity constraint. You cannot move too fast. Okay? Or if you want joint angle constraint, because if you're here, you cannot further move further, right? So you can say current Q is known, plus U times delta T will be my next Q, right? That's my Q at T plus delta T, right? That's my Q plus Q, that's my Q at T plus delta T. This guy has to be bigger or equal Q min, this is Q max. And you can specify acceleration. There's many ways you can play with it, depending on what's your goal. And oftentimes you may also have regularization term. I think you can play with it. So sometimes you have flexibility. So I'm not sure. If I wanted this pen to rotate this way, for example, to achieve some velocity like this here, okay, I can do. Let me think this way. If I want to do this here, instantaneously to my left, this velocity, I can do this way. I can also do this, right? There's different freedom. I can achieve this velocity, okay? But there's some kind of thing I prefer. I don't want to do this. I just want to stand still. I just want to add some kind of a penalty to penalize deviation from desired configuration. So that can be imposed in the regularization term. I'm not sure how much you can get that, but just give you a hint. So there's a lot of, sometimes you have freedom to choose different ways to achieve the velocity you want, but you don't want to reach some kind of configuration that prevent you from further accomplish new kind of demand. You just want to do something simple, all right? So this can be, I would say, maybe, again, example, maybe some kind of alpha, some weight, right? And you want to make sure their desired configuration, let's call that Q hat, is something you want to make sure whenever possible you're here. That's your perfect pose to serve future demand, right? You don't want to deviate too much from it. So that in that case, I would say any deviation from it I will penalize. So next time, currently I'm Q, right? Next time U plus delta T, okay, I want to penalize this term as well. That's also a quadratic term in terms of my decision variable U. And this is given, and this is known at this time, right? Let me draw some. So these are given, this is given by outer loop. This is available from measurement. At any given time, you know your joint position. So that's it. And U is something you are optimized. This is guy is the optimization variable. Optimization variable. Okay. So sometimes you may not be able to perfectly match the demanded Vy. So the overall system may not perfectly track your desired Y, but that's fine. You already try your best. That's a way to divide and conquer. Okay. So that's this part. I think I explored a little bit last time. So today I spent a little bit more time here. And this is the optimization problem I just mentioned. to you. And this is our inner loop. This is our inner loop controller, but this guy is nothing but a differential IK. What does differential IK mean? You give a desired velocity in task space variable. You want to invert it to find the corresponding joint velocity which can produce this desired task space velocity. Okay, that's exactly differential IK. You can use pseudo inverse, or you can use a more general formulation. This is inner loop. Okay. The next more general case is I wouldn't call it more general case, but it's called the acceleration resolved case. In this case, in joint space, in this case, my robot, I assume I can directly control acceleration. And this is Y is also some cos Q. Do you know any robot can have you directly specify acceleration command? Liu Ben? Okay, so typically if you give a robot and if you want to control it, typically the interface is velocity, joint velocity, or even position, right? You don't directly control the acceleration, but this is a model. Okay, this is a good interface for you to generate motion control with torque as input. So suppose that can be done, or you can directly specify it. Let's assume that. So if you cannot directly control joint acceleration, there's too many dots. 2 dots. That's my command. Suppose that's my command. And you can do one integral to get Q dot. Okay, this becomes velocity resolved case. Then you send to the robot, and robot check that it's fine as well. I don't care, or we don't worry about how you achieve the desired acceleration. Just assume if that's the case, we can design it in a more kind of in a linear way. Okay, let's take a break. We'll continue after break. Okay, acceleration resolved control. I think it's I think no kind of robot can directly ask you to interface it with it through acceleration command. Okay. It's not common to see, but it's very important case when you design this kind of a controller. Okay, it's a special abstraction case. Let's just assume you can directly specify joint acceleration. If you say I want joint acceleration to be 2, and how the robot can achieve this, it's something else we do not worry for now. Okay, just assume that you can direct control to the acceleration. So in this case, the state space model looks like this. So Q double dot equal to U. That means this is a double integrator model. Okay, our U is direct control the acceleration. And if you want to track in joint space, you want to track some kind of given joint trajectory, all you need to do is the following. You just say that U equal to desired acceleration, that's a feed forward term, plus some correction term. Okay, so this is the error, right? This is the Q tilde equal to QD minus Q. That's you measured current Q, and you know your desired Q. The deviation from it is the error. So it's of the error times the gain matrix. You generate the feedback control command. And if you're more familiar, this will be, I call it K0 now. This will be KP, right? This is the KD. PD control, right? Position error, velocity error. Each of the error multiplied by gain matrix is almost like a PD control. Okay, if you just do this, you plug in into this formula. Let's call that 4 or 5. Let's call that 5. You plug in this guy into 5. You move this D to move everything. Let me think. Yes, move this part to the right. You got this equation. That's the differential equation governs the aerodynamics. It's a second order differential equation in Rn. So this guy is also in Rn, right? So under what condition it is stable? Actually, you can introduce state. This is not in the standard state space form. You have second order derivative. We want to get rid of the second order derivative so that you have to introduce this in a state variable, right? X equal to Q and Q dot. That's our state vector that belongs to R2N. Okay. And X dot equal to, you know, Q dot equal to Q dot, right? So this is my, let's say X1, X2, and this is Rn. This is Rn, right? So this part is 0. This is the identity. Q dot equal to Q dot. That's the second part of the second half of the state vector. And the Q dot derivative will be Q double dot. And Q double dot, oh, sorry, I have this tutor here, right? The aerodynamics. This is a Q tutor dot. And Q tutor double dot, Q dot. Q tutor double dot equal to negative K1 times Q dot. K0, negative K, so negative K0, negative K1. So overall, I have this is my A matrix. Okay, so it's stable, means error. The error contains position error and velocity error. So the both position error and velocity error will convert to 0 if A is Hurwitz or stable. Stable if A is stable. Anyway, if A is Hurwitz, i.e. eigenvalue of A lies in the upper left half plane. Okay, typical choice, you have diagonal K matrices and all the elements are positive. I think that can guarantee stable. All right, so that's this simple case. This case makes sense. If whatever desired acceleration I tell the robot to do, then the robot, maybe the robot combined with other controller can achieve that desired acceleration. If that's the case, then I can design motion control like that, all right? And the next part will be acceleration resolved case, but in task space. Okay, you don't directly control the joint acceleration anymore. Okay, sorry, acceleration, you don't directly track a joint of a reference anymore. Okay, so the reference I need to track is given in task space. This is or y equal to fq, some task space variable. It specifies the velocity. Sorry, the reference. And so you need to know the input-output relation for your system, right? This is my Q double dot. We assume we can directly control Q double dot, and the Y is my FQ. So I need to know their relation in order to design controller. So we take first derivative, that's our previous relation. I need to know, because do we have control yet? The control now is Q double dot. So we haven't relate output with the input yet by taking one derivative. So I take another derivative, Y double dot, I get this Jacobian matrix dot times Q dot plus Jacobian matrix, analytical Jacobian times Q double dot. And this is our control U. Okay, so now I can do the similar things. All right. Before, I can directly control Q double dot or Y double dot. They are the same in this joint space case. Now, we want to track Y, right? We hope we can directly specify this guy. I call this AY. We hope we can directly control Y double dot, but we don't, right? So all we need to do is the same thing. We introduce a virtual control, which is AY, and we design a control law to design AY. And then the assumption just becomes how I make sure that I can, internal or inner loop can track or achieve any given AY as much as possible. Okay, so I will say, again, introduce a virtual acceleration control, which is A of Y. Acceleration, suppose you can direct control acceleration, which you don't, but just assume that you can do that. Then the rest task is not my outer loop control job, it's your inner loop job. So I tell you AY, you have to achieve that AY. If you don't do it, then we didn't really kind of work. Our objectives are not aligned well enough, right? So introduce a virtual control AY. So we will have Y double dot equal to AY. That's a second order, sorry, the double integrator dynamics for Y. Okay, and then if I can design AY, let me see that. I need to draw the. Okay, so let's draw that figure here. Let me draw that here. Again, this is my robot. The robot actual input we assume so far is Q double dot. Okay, and this is Y here. Now I assume I can, this is outer loop. I assume I can directly control, this is my YD, okay? The outer loop assume I can directly control AY. So we generate AY. And AY generate, this is the inner loop. And the goal of the inner loop is to do what? To make sure this inner control loop behave like a double integrator, the same as the first case. So let me write it down here. So I will say outer loop, choose, the goal is choose AY to track YD, where the dynamics is double dot AY. This is simple. This is the linear double integrator dynamics is just like what we did before. This is simple, but under the assumption that whatever AY I tell you, the inner loop control guy can achieve that AY for me. I just break the job into two parts, right? And the inner loop guy, the inner loop control will choose you, the actual control input, which in this case is Q double dot, to produce this AY. To produce, I would say, Y double dot close enough to whatever AY you specify from the outer loop. This is simple. It's just I design AY, Y double dot, times the velocity error times the KD, times the position error times K0 or KP here. And if I do this, assume that's my control, as if that's my control, I can directly control that, then I have a closed loop aerodynamics second order And this is stable if the same thing here, right? If this A matrix is Hurwitz. Okay, that's my job from outer loop. Outer loop is really easy. It's always a linear control. It does not depend on system dynamics. It only depends on some measurement. As long as you can measure, you can measure this Y, you can design outer loop. Yes. Where? Where is it? Here? Oh, this is the outer loop. There's not a typo. AY is the outer loop control. I wouldn't call it input. Yeah, so this guy is my model. The outer loop assumes the robot has this model, which is Y double dot equal to AY. In this case, AY is my control. All right. I design AY following this model. Fusen, you agree? Okay. This is, yeah, but that's a good question. All right. Do not look at the block. So the outer loop control need to design the control, and that control assumes the model which is double integrator, which is Y double dot equal to AY. Okay. However, Y double dot is not equal to AY. It has more involved dynamics. So that's not my outer loop. That's not the thing the outer loop control need to worry about. That's the inner loop. We try to make sure the outer loop assumption is correct. Okay, so the inner loop goal is what? To choose this U, which is the Q double dot, to match a given AY. Level still have questions? Okay, good. All right. And how to design this inner loop? What's the goal of the inner loop? Whatever AY you tell me, I will just try my best to achieve a desired Y double dot equal to AY. Okay, can we do this? Optimization. Maybe we cannot do it perfectly. Maybe we have more freedom to do it, and so we can have a regularization term. Okay. So you can see from this optimization, that's inner loop design. What does this optimization mean? That's not about the regularization term for now. What does this mean? I want to choose U. If I given U, and this is what the Y double dot, right? Based on my model assumption. This is my Y double dot. I want to make my Y double dot, I choose U to make my Y double dot as close to the given AY as possible. Okay. Make sense? Or you can add on more constraints if you like, whatever constraint you like. So you maybe have Q max, Q double dot. Here the Y is U is Q double dot, mean double dot, things like that. Okay. You can also have regularization term like we discussed before. So that's the inner loop. Now these two work together. The outer loop defines a virtual control, which is acceleration. Assume you can direct control acceleration. And the inner loop tries his best to make sure this assumption holds. It may not be perfect, but try his best. Okay, and mathematically, if the computer doesn't know what's going on, what those symbols mean, right? Mathematically, this looks almost the same as differential IK. It's just a QP. Right? Is this a QP? Maybe Daifeng. In this case, what is known? What is given? So we're optimizing this. This is our optimization variable, right? We are trying to find this guy at any given time instant, okay? At this given time, I know, or Q and Q dot from measurement. If you don't know Q dot, you need to estimate Q dot, but at least you can measure Q. From measurement, these guys are known, so those are things available. Where does this come from? From your model. The Jacobian is based on your model, but it's only kinematics information about the model. So far we haven't, although we have the Q double dot involved, we don't have any dynamics model involved yet, okay? And this is given, it's given from outer loop. Okay, outer loop need to design this guy. You see this kind of inner outer loop go thing is make things a little bit easier to deal with. So at any given time, all these things are known. All you need to determine is U through a QP, which can be done less than 1 millisecond, right? That's standard nowadays. Oh, I explained that here. What? J dot is from, you can derive it. Based on the formula, but okay, in Drake, I think you can calculate this called calculate bias acceleration. I forgot exactly the function name, but you can do this. That's directly from the model. I mean, these are formulas. If you write everything down, there's a cosine Q, sine Q, whatever. Those things can take derivative. You can derive it. That's no problem, okay? You can look for Drake. Drake has, I think, function to compute this term as well. All right, that's the other part. Now we move to the next part, motion control with torque as input, and the famous so-called TSID, task space inverse dynamics control. I think we already learned this now, but I just need to tell you which part means this task space inverse dynamics TSID. Torque as input versus, let's say, versus Q double dot as input. What's the difference? They are equivalent if you know the model, dynamics model. Okay, so let's take a look. You see how they relate. Torque, if you know this Q double dot, you can directly compute how much torque you need, right? Based on this model, but you need to know the model, which is the dynamic model in this case. If you have an acceleration resolved case, I don't need to know the dynamic model. Okay, everything is kinematics level. Okay, so in this case, I can Q double dot and the tau is 1-to-1 correspondent. The reason is this mass matrix is non-singular, is also a positive definite, not the only semi-definite matrix. Fuzhen, do you know why? IMQ, I think I discussed a little bit about this. IMQ is positive definite. Means IMQ for any Q belong to S plus N. Right? Positive definite matrix. Why? You can prove it, right? So you remember our recursive Newton-Euler, Q is summation I, Ji transpose Ji, right? What does this Ji means? The body I's Jacobian. Okay, and you can prove it. This is always, Jacobian may not be full rank, by the way. The Jacobi matrix may not be full rank, but you sum over all the bodies. So roughly speaking, if you all you need to show is what? Is show Q dot transpose MQ, Q dot is always bigger than 0 for any Q dot not equal to 0. Right? It's always non-negative. And that's true because as long as you move one joint, at least that particular body will have a velocity that is non-zero. You know, J Q dot is the body i's velocity, right? If I have some joint moving and that particular body will have velocity which is non-zero, and if you do that, then it will become here. Of course, you cannot have a zero mass link. This guy has to be. This has to be positive definite for sure. It's always true. If you don't have a kind of a massless link, then that's fine. Okay. Anyway, if you just need to know this is the case. So tau and Q double dot can go back and forth. If you know Q double dot, you control Q double dot, almost equivalent to say you control tau. The only catch is that you need to know the dynamics model to do the conversion. Okay, and there's other property I don't want to mention because that's not relevant for us to design this control. All right. You see, I can invert it to find my Q double dot. Okay, so again, in this case, suppose I still let me see that. Okay, so this case I think it's in this case I want to say y equal to q. All right, that means joint space control. In this case, I specify the reference in terms of joint space reference, which is given. So we're given YD, which is almost like a QDT. All right, we want to track it, but our control input now is, in this case, is tau, which is we directly control specified tau, and this is our robot. That's the lowest level we can get to, right? And this is my Y, which is Q. I want to track desired Q. And again, I will just, in this case, I have an outer loop. So tau and Y follows this nonlinear dynamics. Okay, that's my control input. This is my output, Y. Follow this highly nonlinear dynamics. But we can do is that we can still use the acceleration resolved case. Similar to the acceleration resolved case, I can assume I can directly specify Q double dot. Does this make sense? It depends. Depends on whether that assumption can be achieved through the inner loop control. All you make is assumption that I can directly control the acceleration. But if but you can achieve that by given acceleration, I want to match it through some internal control, then that's fine, right? So the outer loop will be AQ, again, the same thing. Double integrator control design. I think I don't want to repeat that. Then you have a stable zero tracking error dynamics. And in this case, the inner loop, what we should do, let me draw it again. So this is my robot. This is the tau I need to determine. And this is Y is the output, right? And there's an inner loop guy. Inner loop guy just produced the desired tau, but the input to the inner loop is my AQ. The acceleration of joint, okay? Given any AQ, my goal is to find tau to achieve it. Okay, and then the outer loop is y goes here, and this is my yd. So the outer loop is still assumed that q double dot can be arbitrarily controlled. And the inner loop will take care of that assumption, okay? So y is q here, right? Daifeng, what's the dynamics inside this right dashed square? Excellent. So this model is used to design this outer loop. That's the plant of my outer loop control design. Okay, if I do this, I can track YD. But that's under assumption, I'm repeating myself, but anyway, that's under the assumption that I have an inner loop can achieve or accomplish whatever acceleration command I receive. Okay, how do we design this actual u equal to tau, right? Based on my model, if you tell me this is my AQ, right? This is my AQ. If you tell me my AQ, I can compute the tau that corresponds to this AQ, right? That's directly from the model, right? It's tau Q. From Q double dot to tau, this is called what? From Q double dot to Q to tau, this is called inverse dynamics. You give a desired motion, you want to find force to generate that motion. It's called inverse dynamics. And the forward dynamics is a simulation. Given force, I want to know what motion it generates. Okay, so this is the ID. So this is exactly, this formula will be exactly the inner loop guy formula, all right? We don't have to do optimization. If everything is perfect, I can use this model. And this control law has a name. It's called computed torque control. That makes sense? The torque is computed based on your desired acceleration. And can you prove this guy will converge or make the tracking error convert to 0? Yes, if everything is perfect. If you need this guy, I can always generate you to achieve this. So essentially it's fine. Okay. So this control law relies on system model, M, C, and G. If this model information are not accurate, then the control will not perform very well. Okay, it really depends on your model information. You bring in model information, you have to make sure that the model information is correct, or you have reasonable confidence about their accuracy. And this is a computer torque control in joint space. And the task space computed torque approach, I hope you can immediately see how we can do it. Okay, the idea easily extend to the task space. I want to emphasize easily, which you may disagree with me, but Ruben, do you think that's clear? Yes. If I have task space, right? What I have is this guy may be a task space variable, y equal to IFQ. It's not directly joint variable. It's a function of joint variable. And I still use the acceleration resolved case. In this case, I just still introduce a virtual control as the acceleration of y, not the acceleration of q. is acceleration of y, you can directly control acceleration in the task space. Suppose that's the case. And the inner loop will just try his best to achieve that. Okay, so in this case, I know in the acceleration resolve case, this is my u, right? This is not my u, by the way. This is now, okay, sorry. U is tau, right? This guy is q double dot equal to m inverse times u is tau minus the Coriolis term times q dot minus q, g, right? So if you like, you want to know here, this is the formula, right? Q double dot in M inverse times U minus C Q dot minus G. That's what I'm writing down here. So if you plug in this formula here, actually you relate Y with U. You relate Y double dot with U, okay? So if I want to say, how to say, I still say I want to directly control Y double dot, okay? And my inner loop goal is what? So the outer loop is designed like this. It's the same as before. The inner loop will try my best to find control U such that given a U, this will be my Y double dot. Okay, Y double dot related to Q double dot, and Q double dot related to U through the dynamic model. Overall, I have a relation from Y double dot to U. So I can choose U to modify Y double dot. How do I modify Y double dot? I want to instantaneously my Y double dot equals to AY from outer loop, okay? So this is from outer loop. Those guys are known, as I mentioned before. Okay, of course, subject to constraint. There are a lot of variations. Of course, we can have 4 or 5 lectures, but they are essentially the same. Okay. So sometimes you can directly compute, or you can make this minimization error equal to 0 if the Jacobian is invertible. But in general, we prefer to use QP or optimization to formulate this. So you don't need to worry about singularities, redundancies, things like that. I want to mention this is already a task space ID already, okay? But it's not in the form that you commonly see from the literature. I just want to mention a few words about inverse dynamics control. Let me draw a figure. So the computed torque approach, let's say, if I draw this from YD, this is the outer loop. This is from AY, okay? That's a desired motion, right? And then this is robot. This is my torque, suppose. From motion to torque is inverse dynamics. From torque to motion, it's forward dynamics, right? So this part, inner loop, it's just inverting the dynamics, almost like inverting the dynamics. If you can invert the dynamics, then this guy become linear. You just have a standard linear control problem, okay? So this part is inverting the dynamics. Oh, I mentioned that here. So given desired acceleration, either in joints at level or in the task space variable, we invert it to find the required control. In this case, it's I'm AQ. task space can be viewed as inverting the task space dynamics. So task space acceleration, you want to find the desired torque to generate that task space acceleration. So this is nothing but TSID. Task space inverse dynamics. It's just terminology. I think you have know the essence of this task space inverse dynamics or joint space inverse dynamics. They are the same. The goal is just break your overall control objective into two phases. You have a virtual control, make everything simple, but assuming you can directly specify the desired motion, which is specified in terms of acceleration. Then the internal control guys just work hard enough to achieve that desired motion, almost like inverting the dynamics. Sometimes the dynamics can be perfectly inverted. Sometimes it cannot be perfectly inverted. You have to have some error. So overall, you hope the error is not big enough. It's not too big so that everything still works fine, right? We want to, let's say, equation 7 is just what we derived right here. This is the inner loop one, right? So we are trying to find my U, which is torque. This is, as I mentioned, this is AY, this is Y double dot, right? So I want to make sure my Y double dot to be as close as possible to the given acceleration demand from outer loop. Okay, that's a task space ID, inverse dynamic control. And this mathematical form, typically we don't like these guys. Inverting the math matrix, things like that. And these two are equivalent. Okay, I just adding a new kind of a decision variable, which is Q double dot. You know what is this, by the way? This guy, sorry. This guy, this part is Q double dot, right? Q double dot equal to M inverse times torque minus that. That's Q double dot. And that involves some inversion, and I can make this problem, I mean, mathematically they are equivalent if I minimize over both U and the Q double dot, but I know U and the Q double dot satisfy this constraint, which is a linear constraint. This is linear constraint in what? Q double dot and U. Q dot is known and Q is known as well. At any given time, this is almost like AX equal to B, things like that, okay? So then I can have a nice form like this. So then it's the same as what you did before for task space ID. Similar. There are many different variations. I just want to make sure, just want you to know that these kind of things are equivalent, and you can make different forms of equivalence to somehow simplify your numerical implementation. This is the dynamics constraints. Okay, I think we're good. Any questions? Was there any questions? Okay. If you see task space ID in the future, in the literature, you should also know you can somehow analyze the stability if you're asked to. Okay. Maybe last time Liuben tells me, oh, I need to make sure I have time for your quiz. This is the outer loop, let's say call that, okay? And the inner loop, and this is robot. Okay, and I assume that Y dot can be completely controlled, right? That's the overall structure. If you're perfectly inverted, to achieve this, then you can, as long as the outer loop can track it, then you're fine, okay? What happens if you cannot perfectly match it? So there may be some response. This is my AY, suppose, I mean, scalar case. This is my AY, but maybe the actual acceleration like this is not perfect. Can you analyze it? Yes, you can. Suppose you can use a second order system, not double. This is almost like a double integrator. If suppose you can approximate this as a second order or third order linear system, and you can start analyzing the behavior as well, okay? So if not perfect, if any desired given AY cannot be perfectly matched, you can do experiment to see how much it can be matched. You model that part and you can prove, or you can design better ways to compensate that discrepancy, okay? That's a little bit more advanced, but more detailed, I would say. All you need to know, I think, is done in this lecture. At least you have a big picture, what are the relations of different motion controllers, okay? Hopefully that's good enough.